So anyway, today I want to finish the sequence of 3 lectures on optimization, and the first and second lectures were on linear programming and the simplex method, and today I want to mostly talk about interior point methods and nonlinear optimization. But before I start the main topic of today, I did want to say just one little thing which I think might be interesting to you. It's related because it relates optimization a little bit to machine learning. And just one slide on this issue or this topic. So a common problem that arises in machine learning is the L1 penalized regression problem, where you basically you have 2 competing objectives. And by the way, having multiple competing objectives is an extraordinarily common thing in all of optimization. And in this context, the competing objectives are that you want to, say, solve a least squares regression problem for some vector x. So we talked about regression the other day, both least squares and least absolute deviations regression. And so you want to minimize, you want to find an x that best, so you want to find an x for which ax is as close to b as possible, using optimization notations rather than statistics notations for these things. Okay, that's one objective, but you also have an objective that you don't want to over fit the model. You don't want x, which are your regression coefficients, to have too many non-zeros, because you put in a whole bunch of things in your model because you're not sure what's relevant, and you're hoping your model will pick out what's relevant. But the reality is, if you just solve the regression problem, everything will be relevant to different degrees, and you would like to more systematically avoid that and force some of those x's to be 0. And so one way to force those x's to be 0, it would be to minimize the sum of the absolute values of x. If you just did that by itself, you would get a big fat 0 for all of them. And so you have these 2 competing objectives, and one of the standard things to do is to introduce a parameter, which we'll call lambda, and take a linear, a weighted average, if you like, or linear combination, I guess in this case, of these 2 objectives, and minimize the weighted average. Now, of course, you don't really know what the right value for lambda is. And this is what always catches my eye whenever I hear statisticians or machine learning people talk about this class of problems, is you don't know what lambda is, and that's a problem. And so I think what most people do, you folks may know better than me and can correct me if I'm wrong, is they simply solve this problem for a value of lambda and see if the solution has a sparsity that they're happy with, and if it's too sparse, they may decrease lambda and solve again. If it's too dense, they'll increase lambda and solve again, and iterate on lambda, solving these optimization problems multiple times. And that's certainly a reasonable approach, but I would like to propose a different approach. And I don't know if this approach has been proposed before. Maybe it has. I'm not sure. But here's what I would suggest. I would change the least squares regression to least absolute deviation regression. I argued the other day that that's a good thing. It's robust regression. It avoids outliers. So I'm always inclined to do that, and I think the main reason statisticians, well, okay, there's more than one reason. A few reasons. I'll mention a few. One reason that statisticians like least squares is because it's that formula that I showed you the other day, and that was easy to solve. Whereas optimization is a little bit more complicated. Although today, the slides that I was just preparing, so I may have to do it on the blackboard, I'm going to show you that interior point methods for linear programming are essentially iteratively reweighted least squares problems. So it's just like what I showed you the other day for the regression problem. So that's one thing. Of course, the other reason statisticians like least squares is because of the central limit theorem and Gaussian random variables. And maybe that's compelling and maybe it's not. Anyway, so I would change it to least absolute deviation regression. And then I would formulate the problem. Now you just have absolute values. There's no squares anymore. You have absolute values here. You have absolute values over here. You have to do the trick that I showed you the other day, and you make this into a linear programming problem. But even better than that, you make it into a parametric linear programming problem. And I showed you the other day the parametric simplex method. And the one I showed you the other day, I was introducing the parameter just as a way of solving a generic linear programming problem. But if the linear programming problem comes with a parameter, and you can think of one value of the parameter where the optimal solution is trivial, then you can start at that value of lambda and use the parametric simplex method with the parameter provided and solve the entire problem for all values of lambda in more or less the same time you can solve for one value of lambda, just doing it in a traditional way. And here we do have a trivial solution. If lambda's huge, like infinity, then the solution is x equals 0. So we know how to start this thing, and we can use the parametric simplex method to solve it for all lambdas. And then you just make a list of all the solutions and look at the one that has the sparsity that seems good to you. You've got them all. You didn't miss anything. So I think that could be a good idea, but I'm not sure if it's been considered before. Okay, interior point methods. So let's talk for a minute or two about what it is that makes linear programming hard. So we have a primal problem, which I've thrown in the slack variables here to write it this way. We have a dual problem. I've subtracted off the surplus variables to write the z's in there. And if we could find an x, a w, a y, and a z, the x and w are feasible for the primal, and the y and z are feasible for the dual, and there's no duality gap, then we've solved the problem. So how hard is that? Well, one way, we could say it just exactly how I just said it. We could write this down and write that down and write that the difference of this is equal to 0 and ask ourselves, how hard is that? It's just a linear algebra problem. There's no maximizing or minimizing when I say that. It's just solving equations, but what makes it hard is that there's inequalities in those, so it's not just equations, it's also inequations. So, well, one thing we can do is I guess one thing I'm going to say is we'll ignore at some point in a minute here the inequalities, and temporarily anyway, make believe they're not there. That will help us write things down. And then if we count the number of equations we have, everything else is linear. So let's count the number of equations. Remember, I'm always using the convention that A has m rows and n columns, so it's m by n matrix. So this is so B is an m vector, and this is m equations. And this is n equations. And then if I said the two objectives have to be equal, that's one equation, and so that's m plus n plus one equation. And how many unknowns do I have? Well, x is an n vector, w is an m vector, y is an m vector, and z is an n vector. So I have 2m plus 2n variables in n plus m plus 1 equations. So that's not the greatest thing around. It'd be nicer if they had the same number of equations as variables. And one way to finesse that is to, instead of saying that the primal and dual objective should be equal, let's say that we satisfy the complementarity conditions. Because as I believe I showed the other day, it's also true that if you're primal feasible and you're dual feasible and you satisfy complementarity conditions, then you're optimal. So that's another way of saying it. And if we take those equations and then throw away the non-negativities and count up equations, we have m here, n here, n here, and m here. That's 2n plus 2m equations and 2n plus 2m unknowns. That's kind of a nice situation to be in. Let me go back here. So that seems pretty good. Of course, we've left off the inequalities, so it seems a little bit scary that we're doing something wrong here. But in a way, the complementarity is capturing the fact that 0 is a boundary in some sense. And it seems like we're on the right track here. But there's another problem, and that's that these are nonlinear. So just because you have 2n plus 2m equations and the same number of unknowns, that's good for linear algebra, but for nonlinear algebra, it's a little bit more problematic. But anyway, that's where we want to head here. So I want to have some notation and do a little bit of algebra. And the notation's a little bit funky. It was invented in the early days of interior point methods. I think it was by Mike Todd, but I could be wrong. In his first paper, he certainly used this notation, and I don't remember it being before that. Anyway, here's the idea. You want to write things like x times z equals 0. Various people have made various ways of doing this, where x and z, of course, are vectors. And so the notation that's become popular in interior point methods and optimization in general is if you have a vector x as a lowercase thing, then you can make a matrix out of it by making an uppercase x and just put the vector along the diagonal and zeros elsewhere. And if you are willing just to do that little trivial notational weirdness, then you can write the complementarity conditions in a very simple way, because the product of the diagonal matrices gives you a diagonal matrix with the products on the diagonal. And then if we multiply this by E, which is the vector of all ones, that takes the diagonal matrix back into a vector. And so that's how you make the vector of all products of the components. So that's just a notation that's standard. Could be written many different ways. So our complementarity conditions algebraically are written like this. And so here we have our conditions, as I was saying before. We have the equality constraints of primal feasibility, the equality constraints involved in dual feasibility, the complementarity constraints, and then all the inequality constraints. And this is what we want to solve. There's no optimization. If you solve this, you've solved the optimization problem without optimizing anything. And so as I was saying before, we want to temporarily just ignore the non-negativities and consider this system of 2n plus 2m equations and 2n plus 2m unknowns and try to solve them. But, as I was saying, they're not linear. So, finding the roots of things, you basically use Newton's method, and I could pose the next step as we're doing Newton's method, but it's so close to being linear, it's actually just easiest to write down the approximations and see how it goes. So, anyway, but the conclusion of what makes linear programming hard is it's the nonlinearity of the complementarity conditions that fundamentally make linear programming hard. And those complementarity conditions come about because of the inequalities, and that 0 plays a special role. Other than that, linear programming is no harder than solving a system of equations. Okay, but we have to address this minor difficulty. Now, x times z equals 0 is saying that x is equal to 0 or z is equal to 0, or both. If I plot just one component, say, and the corresponding component of z, x times z equals 0, if I plot it, it's just this. And so we're saying we're either here or here. And it's kind of a non-smooth condition. And so it's nicer to relax that condition a little bit and say that the product should be a small constant. So by writing xz e equals mu e, I'm saying each of the products, zj times xj, should be equal to mu, where mu will be a small constant. And in the algorithm, we're going to let mu go to 0 as we iterate to get closer and closer to solving what we really want to solve. And so this is called MewComplementarity. It's a relaxation of complementarity. And if we plot the equation like that, for mu, for some value of mu, it's a hyperbola. Oh, of course, it's 2 hyperbolae. It's this over here as well. But that's a little bit smoother. We don't have this kink. And we can do calculus type things. So, here's the algorithm. Start with a guess. And I hope it's not confusing, but I'm just going to call my guess x, y, w, and z. Maybe I should put some superscripts here to indicate that this is on some iteration 0 or something. I'd put a little superscript on there, but I'm going to just leave those off to keep it simple to read, but I hope it's not confusing. So these are particular guesses as opposed to the x's up here, which are the variables, which are variable. Here my computer program will pick values here. In fact, generally speaking, the initial guess, it's often good just to take all these things equal to 1. But anyway, we have some guess. And from that point, x, y, w, z, we're going to step to a new point. And the new point is going to be x plus delta x, y plus delta y, w plus delta w, and z plus delta z. So we're going to introduce these step directions that tell us which way we're going. And we want to pick them intelligently. Well, the most intelligent thing to do would be to pick them so that they satisfy this equation exactly. So if we substitute that in, just plugging, instead of x, I plug in the new point, x plus delta x, and so on and so forth. Everywhere up here, I plug it in, I get this system of equations. Which, okay, let's look at that. If we rearrange it, well, let me go back to it. I mean, if we, we're thinking of x, y, w, and z now as given. They're guesses of the solution. And so in this system of equations, it's the delta variables that are variables that we want to solve for. There's 2n plus 2m of them, and we'd like to solve for them. But they still appear here in a nonlinear way because I have delta z times delta x, and I have delta w times delta y. But what Newton's method does is it linearizes the system of equations, and basically, in this context, all Newton's method does is it says, you see that product there, delta z times delta x, just ignore it, throw it away. Those are higher order terms in your Taylor expansion, and same with the delta w times delta y. We'll just throw those away. And since we're thinking of this as a system of equations in the delta variables, we'll put everything else that doesn't involve the delta variables on the right-hand side to make it, the usual kind of thing. The variables on the left and the constants on the right. And so, writing it out, it looks like this. So this is the system of equations we want. And because I've dropped the nonlinear products of the deltas from these last two equations, this is now a completely linear system in the delta variables. So we can solve this linear system. And we could take a step to that new point. And then we could iterate. And there's all kinds of theorems about Newton's method and when it converges and when it doesn't, and so on and so forth. And so we could invoke those ideas and try to prove something here. But we do have to remember that I've dropped the condition that x be greater than equal to 0, y be greater than 0, and so on and so forth. And we can't just let go of that completely. And so here's how we bring it back. We start somewhere, as I said, at x, y, w, and z. We figure out what x plus delta x, y plus delta y, and so on would take us. if some of those values, if some of the new values would be negative, then we shorten our step length to keep all the new values positive. The original values were all positive. I think I forgot to emphasize that, but it's probably written here. The initial values must be positive. So we're going to start it with all those inequalities being satisfied, and we're simply going to maintain that property throughout. And so we just have a damping factor, theta, that keeps all these, it's the same theta for every component. And in fact, what you do is it's similar to the simplex method, where you figure out what thing hits 0 first. In the simplex method, it guided us in the choice of a leading variable, and then we did our pivot, and that thing actually went to 0. Here we don't want things to actually get to 0, but we do the same kind of analysis. We see which ones would get to 0 first. We ask how big of a step, or really, how far past 0 it would go, and then figure out a theta value that would get that maybe only from where you started to maybe 90 or 95% of the way to 0. So you figure out this theta. It's a very simple little ratio kind of calculation, very much like what we did in the simplex method, and to keep everything strictly positive. And in practice, you let things go about 90% of the way to 0 or something along those lines. Okay. So these are the slides I was working on when I got called to service here. So I'll switch to the blackboard for a minute and a second. So let's see. So here's our equations. Let's talk about solving this system of 2m plus 2n equations and 2m plus 2n unknowns for a second. We can actually simplify it a bit, or do part of the solve quite quickly, because the last two equations are really quite simple. This is n equations, and it involves, say, the delta z variable appears in just, each delta z1 appears in the first equation, delta z2 in the second equation, and so on. And so this is very easy to solve for delta z. Or another way to say that is, the matrix, this is a diagonal matrix X with all positive entries by assumption. And so that's an invertible matrix. And so I can solve for delta z like that, just solve that equation. Similarly, with the last equation, for this exact same reason, because the y's are all positive, I can solve it for delta w in terms of delta y. And here's that equation written out. And if we then substitute delta z into the second equation and delta w into the first equation, the first two equations, and then rearrange things a little bit, putting the things that don't involve deltas on the right and keeping things that do involve deltas on the left, we get this smaller system of n plus m equations and n plus m unknowns. And it is a little bit of work because it involves this non-square matrix A and A transpose. And so going further is a little bit harder, but doing this is simple. So this is called the reduced KKT system, or the reduced KKT system, Kuhn-Karush-Tucker system. But let's talk about solving it even a little bit further. We can actually do something here, and that's what I didn't quite get a chance to type up. Erasers are somewhere. Okay, so let me write that in block matrix notation here. Let's see. So I'm going to have a delta x and a delta y. And on the right-hand side, I'm going to have, you know what, I don't really care what I have on the right-hand side. Let me just call that rho and sigma. That's just data. Just a calculation. So, and what do I have here? In the first equation, I have, oh, I want to write the second equation first. So that's A transpose delta, no, I don't want A transpose. Oh, wait, I'm writing it first, not second. Yes, I want it first. A transpose delta y in the second equation, and x inverse z. X inverse z times delta x. So x inverse z delta x plus A transpose delta y, and I guess I would rather call these, to keep them consistent with what I usually do, sigma and rho. And the first equation, which I'll write down second, is A delta x and minus y inverse w delta y. And so we can reduce this a little bit because this is a diagonal matrix. It just has the components zj over xj on the diagonal. I could use the first equation to solve for delta x and then eliminate delta x from the second equation. So what do we have here? If I solve the first equation for delta x, what do I get? I've got sigma minus A transpose delta y. And then I have to multiply by the inverse of this, which is xz inverse. So that's my delta x. Did I screw up? This is delta y. Is that what you're saying? Yeah. And now I plug delta x in. That was, I just solved which equation? The first equation. Now I plug delta x in the second equation, this formula, so I get A times xz inverse times sigma minus A transpose delta y minus y inverse w delta y is equal to rho. And now I bring the things that don't involve delta y over to the right-hand side, and I get what? So on the, oh, is everything got a minus sign? Oh yeah, I guess that's right, I forgot. Well, what do we have here? We still have a minus A xz inverse A transpose delta y on the left. That's this times this. We also have a minus y inverse w delta y, and that's going to be equal to rho minus A xz inverse times sigma. And have I got it right? Okay. And now this is just multiply through by minus 1, and this is just A xz inverse A transpose plus y inverse w times delta y equals the same thing. And now we stick that in for delta into our equation for delta x, and we finally get for delta x a formula that's xz inverse times sigma minus A transpose times delta y. Oh, wait a minute. I haven't solved for delta y yet. I have to multiply by this inverse to get delta y. So yes, so I'm plugging in for delta x, and I need delta y here. And so it's this matrix inverse times that. So it's this matrix inverse times rho minus A x z inverse sigma. And oh, I have a minus sign wrong? Where's my sign wrong? This is plus? Oh no, rho's minus. Both of them are minus, right? Oh, because of this minus you mean.
you multiplied by -1, and you didn't multiply the right side. You just...
Yes. Yes, yes, yeah, oh yes, yes. So rather than doing this, I'll rewrite it. So this is minus rho plus, right?
Yeah.
And so this is a minus and a plus. And for problems with equality constraints, and lots of problems have equality constraints, this matrix actually comes out a little bit differently. When a problem has equality constraints, there's no slack variables on the primal, so the W is equal to 0 in that case, and basically everything else is the same. Oh, I missed the E, right? Oh, no, that's right. And so this term would go away, and let me see if I can write this out in a little bit more detail. So it's xz inverse sigma minus A transpose, and then it's just this matrix, A xz inverse A transpose inverse times a minus rho plus A xz inverse sigma and also, so I'm assuming equality constraints which means W is equal to 0. Let's also assume that we had a feasible initial solution. So we're doing something like the primal simplex method, something analogous to the primal simplex method. We're going from feasible to optimal. If we assume that we could start out feasible, that means that rho is equal to 0. And so if we have that, then this rho is, where am I here? The rho is gone. And what I wanted to say is this looks almost exactly like, and in fact in some cases it is exactly like, iteratively reweighted least squares all over again. So I showed the other day that for least absolute deviation regression, we can solve it either as linear programming or as iteratively reweighted least squares. But the point here is interior point methods for linear programming are iteratively weighted least squares of a type. But what we didn't have before was we didn't know when to stop. You know, I just said iterate, you have to go forever. But with interior point methods, we have duality theory, and we can say exactly when to stop. So that's a big advantage. Okay, so I just wanted to make this connection that interior point methods are a flavor of iteratively reweighted least squares. And just to put another buzzword on it, one of the original interior point methods was called the affine scaling method. And the affine scaling method has some of these simplifications that I've briefly alluded to. And in the affine scaling method, it is exactly iteratively reweighted least squares. Okay, so here's what we do to finish this up. We iterate this thing. So we pick a smaller value of mu for the next iteration. And we just repeat exactly what we said from the beginning until our currents, we just keep doing this over and over again until we satisfy the conditions that we know from duality theory, that the primal should be feasible, the dual should be feasible, and the duality gap should be basically 0. Of course, all these things, if you really want these to be 0 exactly, you have to do an infinite number of iterations, just like I said for the iteratively reweighted least squares before. But on a computer, everything is finite precision, and so you say, okay, I'll go to 8 digits of precision or something like that, and so you put an epsilon over here on these 3 things, and you just stop when you get to some reasonably small tolerance. Okay, so there's a theorem which I'm not going to prove, but let me at least state it to give you a flavor of how this all goes. If you do the algorithm I just laid out, which is quite simple, you can. It's actually an easy homework problem to show that the primal infeasibility goes down by a factor of 1 minus theta at every iteration. And the dual infeasibility goes down by the same factor at every iteration. And those two are really easy to prove. They're just a few lines. The third one's not hard either, but it's a little bit trickier. If the primal and the dual are feasible, then the duality gap decreases by a factor of 1 minus theta at every iteration. And that's assuming mu is equal to 0 to get that actually. And when mu is positive, it's a little bit slower in convergence than that. So this tells us how the algorithm works. Theta was how much I had to shorten my step to keep everything positive. Newton's method told me let theta be equal to 1. That's a full Newton step, but it might take some variables negative, so I have to shorten it. But I'd love theta to be equal to 1. And this theorem here tells me if I could let theta equal 1, then in one step I would be exactly primal feasible, exactly dual feasible, and then in the second step I would get duality gap going to 0. So if I could have theta equal 1, I could, for 2 iterations in a row, I would be done. But because of the non-negativity, theta can't be equal to 1 ever, basically. So it's an iterative algorithm. All right, so it's hard, basically impossible to expect anybody to do these interior point methods by hand because it involves inverting big matrices at each iteration. Yet it's easy to program a computer to do it, of course. I should say, in practice, these interior point methods make a lot of progress quickly because you're starting out inside the feasible stuff. Well, if we're doing the feasible thing, but you're starting far away from the non-negativity constraints. Let me put it that way. You start far away from the non-negativity constraints, and those are the only thing that stop you from going just 2 steps to the optimal solution. And if you start far away from them, you make big progress in the first iteration, and you make substantial progress in every iteration, and you home in on the right solution, which will be on the border on the boundary of that set. So, as you iterate, you get close to the place you don't want to be. So the simplex method followed vertices, whereas interior point methods, maybe I should have used the black one. Maybe that's enough space. I'll switch colors. So in the simplex method, if we just had a 2-dimensional polygon, and this was our feasible region, if it was maybe that's not a good color. If it was the primal simplex method, so we would start out feasible and iterate. We might start out here, but the optimal solution's over here. The simplex method iterates like from here to here to here, and then you declare yourself optimal. And in 2 dimensions, that doesn't seem bad, but in high dimensions, the word on the street is that there's lots of edges to get around a polytope, and it can take a while. Whereas an interior point method, if we start it feasible anyway, starts like this, and maybe you didn't get lucky and started exactly in the middle. That would be maybe too good. you start somewhere like this, and it more or less points in the right direction. And you take you take a step like 90% of the way until something gets violated, which would be that edge there, and then you take a step that goes 90% of the way until something gets violated, and it goes in like that. So in this little two-dimensional problem, the simplex method only took 3 pivots, and the interior point method will take more than 3 pivots, so the simplex method looks more compelling, but the two-dimensional picture is deceptive. In reality, as I think I convinced you the other day, the simplex method takes n plus m over 2 pivots or something like that. So when m and n are large, the simplex method takes lots of pivots. Whereas the interior point method is extraordinarily robust. It takes 20 iterations. I mean, it depends on how you set your epsilon tolerances of when you want to stop. But with reasonable tolerances and double precision arithmetic on modern computers, it takes roughly 20 iterations. And then, of course, some problems are harder and some problems are easier. It's not a guarantee. And by the way, that's a practical statement from real experience. The complexity bound is that it takes square root of n iterations. Which does grow with n. But in practice, it stays basically constant with n. And so the simplex method might take several thousand, or this might take just 20 of these. But the work per iteration to do this is inverting a system of equations. This is a m by m system of equations here that you have to invert or solve a system involving it. And that's more work than one pivot of the simplex method. One pivot is like just part of a Gaussian elimination step where you'd have to do n of those Gaussian elimination steps to solve a system of equations for an n by n matrix. So a pivot is a much smaller operation than a matrix inversion or matrix solving a system of equations. And so even though it takes very few iterations, it's deceptive because they're expensive iterations to do. The original hope was that parallel computing would come to the rescue here. And the simplex method is sort of inherently sequential. I can't go from here to here until I know that I got here to start with. And so the simplex method is inherently sequential. Well, of course, the interior point method is also inherently sequential, but inherently sequential of order 20 rather than having to do several thousand things. And if I could make each of these things a lot faster, then I could do this quickly. Whereas what's going on in a pivot is a smaller amount of work to start with, and so there's less opportunity to parallelize that on modern computers. But that's proved to be rather difficult because you're trying to do this quickly in parallel computing, where A is a sparse matrix, X are diagonal matrices, A transpose is just a transpose of A. So that's a sparse, that's a matrix, and you want to treat it sparsely, and you want to exploit the sparsity, and exploiting sparsity and at the same time benefiting from parallelism, parallel computing is difficult. So, okay, let's go back to the slides here. So I just had a printout here of my code solving a problem. This particular problem had 1,350 variables, 146 constraints. My code is general in that it allows for variables to be non-negative, or they can be not non-negative. They can be what we call free. They can be positive or negative, or they can be bounded, which means they have an upper and a lower bound. And so these are treated a bit differently, and so my code reports the breakout here. And also the constraints can be equalities, inequalities, or what we call ranged, which means it's a two-sided inequality. The constraint can't be above this and below or below that. So this problem had 146 equality constraints and 1,350 non-negative variables. But look at the A matrix here, has only 5,288 non-zero entries. So that per column is about 4. This has 4 non-zeros per column. So the A matrix is extraordinarily sparse. And so the code exploits that. And it took, this particular problem took 15 iterations to solve. And at each iteration, I print out the primal objective value as you currently have it, the dual objective value as you have it, the primal infeasibility, so that's basically the norm of the vector rho. The dual infeasibility is the norm of the vector sigma. And as we know, we have to be primal feasible, so this number has to get small. We have to be dual feasible, so this number has to get small. And there has to be zero duality gap, so the difference between these two numbers has to be small. And these are the statistics that I summarize over here. So DF means dual feasible. So once this number gets below 10 to the minus, I think I have 10 to the minus 6 as my default, I declare the problem dual feasible, and similarly with the primal feasibility. So here I'm not primal feasible. Oh, I guess I use 10 to the minus 5 as my threshold. Here I am primal feasible. And so these, but you can see it did much better than just that. It got way down to 10 to the minus 12 and 10 to the minus 15, which is almost machine precision. And the objective function values have to get, this column here reflects the objective function values, how many significant figures of agreement there are between them. And my rule is you have to have 8 digits of agreement between the objective functions. And so when you have 8 digits of agreement and you're primal feasible and dual feasible, you stop and declare yourself optimal. And you can see that this is behaving, as I indicated before, that the infeasibilities drop dramatically fast, right from the beginning. Though my step length here is, I think, 99% of the way, so it can go quickly. But the objective function values, they sort of don't do much until you start getting close to feasibility. And so, around here, where both the primal and the dual are starting to get close to feasible, that's when the objective function, the complementarity starts to kick in, and we start to get close to optimality. And so these numbers come in. These things always start in later than getting feasible. And that's what that theorem was telling us before. Okay. Let's see, I started a few minutes late, but should we take a break? Oh, actually, maybe, I'll finish a few more slides and we'll take a break. So this whole idea, I'm going to generalize to nonlinear programming in a few minutes, and so let me give you the framework that's natural for the purposes of generalization. So if we start with an optimization problem in our favorite form, like this, standard form, and introduce our slack variables like this. And these are the same steps we're going to do in nonlinear in just a few minutes. We're going to start with a problem. We're going to introduce slack variables. And here's the next step that you haven't seen, but we're going to get to the same place. If we replace the non-negativity constraints with the logarithmic barriers, so in other words, I have xj should be greater than or equal to 0. And that's a problem. So here's another way of thinking about what to do. Separate from everything I've said before, gets to the same place though. Replace xj greater than or equal to 0 with something in the objective function. Logarithm of xj. So the logarithm of xj goes to minus infinity when xj goes to 0. And I'm trying to maximize. And so when this goes to minus infinity, that's a pretty strong incentive to not go to 0. And so these are called logarithmic barriers because you introduce a smooth function that keeps you away from the bad thing happening, hitting 0 exactly. And we put this parameter mu here in front. As mu gets smaller, this barrier to hitting 0 becomes less and less strong, and so we get closer and closer to 0. And we do the same thing with W here. And now we've gotten rid of the inequality constraints. And now we do standard technique from calculus, is when you have equality constraints, what you probably all learned in calculus is that you introduce Lagrange multipliers. Turns out the dual variables are the Lagrange multipliers. So if I back up here, I had this system of equalities here that I want to have. There's m of them, so I need a Lagrange multiplier for each of them. Let y be the Lagrange multiplier. And so y transpose times b minus ax minus w is the Lagrangian term that you have to, the term that you have to add to make the Lagrangian. So this is our objective function. These are the Lagrange multipliers. This is the Lagrangian. And what you learn in calculus is set the derivative of the Lagrangian with respect to every variable equal to 0 and solve that system of equations. So if I take the derivative with respect to x, it's really a gradient if you like, but anyway, differentiate with respect to x, this gives me the vector c. The derivative of the logarithm is the reciprocal, and that's, and so if I write this in vector notation, if I write it in scalar notation, this is cj plus mu over xj. Oh, maybe I should use a different letter than j because I have that j there. Let's suppose I'm differentiating with respect to variable xk. This is ck. This would be ck plus mu. This sum would be all 0 except for a 1 over xk. And this would be all 0. This is 0. Here I get the kth row of A transpose y. And this last part is 0. Anyway, if I just write that back into vector notation, it looks like this. And similarly, if I take the derivative with respect to w, there's no w here, there's no w here. This here gives me the same idea as before. I'm going to get like a 1 over wk when I'm differentiating with respect to wk. All the other terms in the sum go to 0. So I just get mu over wk. And the only other place that w appears is in this last one here. And so that's just going to give me minus yk. So I really have mu over wk minus yk equals 0, and that's true for all k. And just writing that as vectors rather than as scalars is just mu times w inverse e minus y equals 0. And of course, the Lagrangian one is, the Lagrange variables one is always the easy one, because all it does is it re-extracts the original constraints. Seems kind of silly almost. So now we get this system of equations. Nonlinear system for x, y, and w. And the next step, which is perhaps the only non-obvious step, is to introduce variables for x, z inverse e. And so we let z be mu x z inverse, mu be x inverse e. And now write out these equations and this equation as a set of 4 equations. So the first equation is just c plus z minus a transpose y equals 0. The second equation is this one here, where I've multiplied by x on the left and wrote this as capital X, capital Z, E equals mu E. That's just this equation rewritten. And I did the same thing with this equation. I multiply by capital W. That's just a diagonal matrix. So this becomes mu E minus WY. But little y is just capital YE. So, that's just that. And the last equation is just the last equation. So, now look at that. That should look familiar to you. It's the same system of equations before. It's the equalities of primal feasibility, the equalities of dual feasibility, and the mu complementarity constraints. Oops, so let me go back here for a second. So, so this is a way to get to these optimality conditions sort of in a systematic way, and we can apply it in nonlinear in just a few minutes. Just to briefly show a plot of as mu gets smaller, it looks more and more like something that has no effect except for blocking you from going to zero, or eventually it rapidly goes to minus infinity. So for very small values of mu, the effect of that parameter, the barrier terms, gets smaller and smaller. But for every value of mu that's positive, it does eventually prevent you from hitting zero. And I think you all know Lagrange multipliers, so maybe I'll not dwell on that slide. So let's take a break.